All right, welcome everyone. Today we're going to keep talking about sequences, and we're going to see a few different strategies and techniques for how to calculate their limits. So we started talking about limits the other day. Today we're just going to see a few more strategies and techniques. And we're going to start by discussing continuous functions. So we know from Calc 1 that continuous functions they work nicely with limits. So we have this result. And what does it say? It says if we have this continuous function f, and we know it's continuous at this number x equals L, and we know the limit of an is equal to L as n goes to infinity, well then the limit of this new sequence, f of an, also must be going to f of L. So what we have here, this function f, is, we think of it as an outer function. So we know continuous functions work nicely when we have like compositions. And that's what we have here, is we have a composition. So f is our outer function. And then inside that outer function, this is where we're going to see our n terms. All right, so we have this new sequence. So how we're going to use this result is we're going to be presented with a sequence where there's an outer function, and then there's going to be some n terms inside that outer function, and we want to calculate the limit. So how does this result work? Well, what it essentially says is we can essentially take this limit and move it inside that continuous outer function. So we can look at just the limit of those inner terms. This only works with continuous functions, and the continuous function, it has to be defined at this number L. So if we think of it, if we maybe write this slightly differently, let's rewrite it with where we've actually moved the limit through. So another way to think of this is the limit of f of an as n goes to infinity is equal to f with the limit now inside. And we can do the limit of those n terms inside, and whatever we get, well, it's just plugged into the function L. So let's see how this works. We're going to try using this theorem in the next example. So let's look at it. We're going to calculate the limit of natural log of 2 plus 3 over n plus 5 over n squared. And we're doing the limit as n goes to infinity. And so when we look at this, we have that setup. We have this outer function. And we know natural log is continuous. It's continuous on its domain. So that's always good. And then what do we see inside that outer function? Oop, I don't want to. There we go. What do we see inside that continuous outer function? Well, that's where we see all of our n terms. And they're inside. All right, so we know our natural log function, that outer function, is continuous. We see all of our n terms inside that outer function. So what we're going to do is we're going to use that result to essentially just focus on calculating the limit of those inner terms. So I missed the punchline. we gotta erase that. Here we go. Natural log. We're bringing the limit inside the natural log function. and we're going to do just the limit of those inner terms. So 2 plus 3 over n plus 5 over n squared. And we're just focusing on doing the limit of those inner terms. All right, so maybe there's a little question mark here. We don't necessarily know we can do this yet because we don't know what we're going to get from this limit. So if we were going to get, say, if we were going to do this and get 0, well, that's no good because natural log of 0 is undefined. So there's a little hesitation here to put the equal sign because we don't necessarily know what we're going to get yet. So we might have to come back to this step if we got something that doesn't make sense. But let's keep going, see what we get, and hopefully everything turns out okay. All right, so let's use some of our limit laws. Our limit laws let us split the limit up over those addition signs. So we're going to do the limit of 2 as n goes to infinity, plus the limit of 3 over n as n goes to infinity, plus the limit of 5 over n squared as n goes to infinity. And we know limit of a constant 2 is just 2. Constant doesn't change, it just stays constant. And then 3 over n, this is one of our constant over infinity forms, so these both go to 0. Both of those fractions with n in the denominator both go to 0. So just a reminder, we have two c over infinity forms. And they both go to 0. All right, so we have natural log of 2 plus 0, which is just the natural log of 2. And we've calculated the limit of those inner terms and found that it was 2. And natural log of 2 is defined. That makes sense. So that's our answer. And we can actually kind of erase that question mark here. This equals sign was okay. So there was a little hesitation because we weren't quite sure what we were going to get, but we actually found that we got something meaningful. So that's our answer. All right. So, recognizing continuous outer functions can be helpful. All right, let's try another example. We're going to do the limit of n cubed over the square root of n plus 5 as n goes to infinity. And we're going to kind of use a couple strategies here. So first, we see that we have powers of n on both the top and the bottom of this fraction. So we're going to go with our usual 1 over power of n method. So we identify the largest power of n in the denominator, and then we divide everything by it. So I want to divide each term that I see in the denominator by my power of n. So I'm going to divide n by n, and then I'll divide 5 by n. And so what I've done here is I've divided each term by n in the denominator, except it's underneath the square root. So essentially what I've actually done is I've divided each term by the square root of n. And so if I do that to the denominator, I have to do that to the numerator as well. So I'm actually dividing by the square root of n, because when I divided by n in the denominator here, those n terms were underneath the square root. So I'm actually dividing by square root n. All right, let's clean this up. So that's one of our usual methods for dealing with these fractions where we have powers of n on both the top and the bottom. Clean this up a little bit. N cubed divided by the square root. Let's simplify that into just one power function. So that'll be n to the 5/2 power. And then in the denominator, we get 1 plus 5 over n. All right, so let's think about what's happening here. So let's consider the limit of the numerator and the limit of the denominator. And let's start with the denominator. So let's look at just the limit of the denominator. What's going on there? So we're doing the limit of the square root of 1 plus 5 over n. And we know square root is a continuous function, so on its domain. So we have this continuous outer function, and then we have some terms inside of it. So we can use that continuous function property that says, let's bring that limit inside. So we can bring it underneath the square root there. Again, there's a little bit of a hesitation there because we don't necessarily know what we're going to get when we calculate the limit inside. So we might have to come back. You know, if we were going to get like a negative here, well, that's no good. We can't have negatives under the square root. But as we're going to see, we have the limit of a constant 1, and then we have this limit of this 5 over n term. That's one of our c over infinity forms. And we know that goes to 0. So this ends up equaling the square root of 1 plus 0, which is just 1. So what's happening in the denominator here is this denominator is as n gets larger and larger, this denominator term is getting closer and closer to 1. All right, what's going on in the numerator? So we know our denominator is it's getting closer and closer to the number 1, but let's consider what's happening to our numerator. And n is getting large positive. So what happens to a large positive number when we raise it to a positive exponent like this? Well, it also gets larger and larger positive. And we say it goes to infinity. So the limit as n approaches infinity, n is getting larger and larger positive, well, then n raised to the power 2.5 essentially is also getting larger and larger positive. So we say it goes to infinity. It's equal to infinity. And so what we have here is an infinite limit. Just means it's getting large positive. If it was getting large negative, we would put minus infinity. But if we go back to our fraction here, what we have is the denominator is getting closer and closer to 1. The numerator is getting really large positive. So what happens to this fraction overall? It gets really large positive. And so that limit overall goes to infinity. All right. So just another example here. This is, I think, our first time we mentioned this infinite limit notation. Really, it's the same thing that we saw when we were talking about limits for real variable functions. So we know a real variable function, if it just gets large positive, we would say that the limit is equal to infinity. Or if it was large negative, we would say minus infinity. And then we were able to use that continuity property here for continuous outer functions. All right. Oh, this is a fun one. So this is another strategy that sometimes can be helpful. So we have this theorem. It's got its own name called the squeeze theorem. And I think this is one of the best named theorems. It's very descriptive. So when we look at a picture of what's going on, you'll kind of see why it's called the squeeze theorem. But what does it say? So given we have 3 sequences that we're working with here, and they satisfy this inequality. Our sequence AN is the terms in our sequence AN are less than or equal to the terms in our sequence BN, which is less than or equal to the terms in our sequence CN. And this inequality holds eventually. So there might be a couple terms at the beginning of each sequence where the inequality doesn't work. But eventually, if we go far enough into our sequences, eventually this inequality holds for all n. So if we have that condition, and we know the limit of sequence AN and the limit of sequence CN are equal to each other, and they're equal to some number L, well, that kind of forces Bn. It's stuck here in the middle, kind of squeezes it, and so the limit of Bn has to exist, and it's actually equal to L as well. So to kind of see why this happens, this is not quite a proof, but it's kind of gives you an idea of why this would be true. If you start with your inequality and just apply the limit to all three sides of that inequality, this inequality. So let's apply the limit on the left. Let's apply the limit on the middle. And the limit on the right side. And the nice thing with limits is if this inequality, well, we know this inequality is true, and if these limits exist, then the inequality must also hold for those limits. And so we know the limit of AN is equal to L. We have the limit of Bn, which we don't necessarily know yet here, stuck in the middle, and then we know the limit of Cn is also equal to L. And the only way we can have this statement where we have some number is simultaneously greater than or equal to number L, but less than or equal to some number L, the only way that can happen is if it's actually equal to that number L. And so we get our result. So this theorem actually says a little bit more. It says we're not even guaranteed at the beginning here that the limit of Bn exists. So we actually get a couple things here. We're told that the limit of Bn, which for all intents and purposes might just do its own thing. It might not exist, but it actually does. And it's equal to that same number L. So this actually tells us quite a bit. Now, why would we use this? Generally, we use this if we get stuck on, we're trying to find the limit of that sequence in the middle. And it's kind of a tricky sequence to look at. And we can, so when to use this? This might be worth writing down. So the sequence we're trying to do is tricky. And the goal is ultimately to kind of simplify it. So you get these two sequences on either side of it that are related, they look similar, but they're just easier to work with. So sigma B, or sequence Bn is complicated, and we want to simplify it. So that maybe there's like one term inside our sequence where that term is just, it's just we don't know what it's doing exactly. If we could just get rid of it, we know what everything else is doing. And that's kind of when you want to use squeeze theorem. And that's what we're going to see in the next example, actually. So we're going to, in example 5 here, we're going to look at the limit of cosine n over n squared as n goes to infinity. And we'll come talk about this graph in a few minutes. But let's kind of look at this sequence. And cosine n is kind of the term here that really complicates things. So that cosine n term, it oscillates back and forth like we know cosine does, usually does. But there's no real specific pattern for how it does that oscillation. So we know cosine n, we know what cosine looks like. It's just it kind of bounces back and forth between -1 and +1. But when we look at just the integer values plugged into cosine here, cosine of n, it's still going to have that kind of usual oscillating that we know, but it's just not consistent enough where we can really predict what the nth term would look like. So if we could somehow get rid of that cosine term, it kind of makes this difficult. And cosine n on its own just diverges. And actually sine n is very similar. Cosine n and sine n on their own diverge. So we can't even look at just the limit of that by itself, because by itself that thing diverges. So this cosine term, really it's tricky because it's oscillating back and forth, not really consistently, and because of that it diverges. It never actually approaches one specific number. So we're going to use the squeeze theorem. And if we could just get that cosine term out of there, it would make things helpful. And we can do it. So there's a trig, it's a trig inequality that's true for both cosine and sine. So we know cosine of n, and cosine in general, is the lowest it ever gets is -1. And the largest it ever gets is +1. And that's true for sine as well. So cosine and sine are always stuck in between -1 and +1. Well, now if we kind of make this middle term, make it match with what we have up here, with what our original sequence looks like, we can do that. We can just divide everything here by n squared, and the inequality is still true. Because we're dividing n squared is positive, so we divide everything by positives, preserves the inequality here. And now we have this complicated sequence term in the middle, and we have these easier terms on either side of it. And we know the limit of 1 over n squared goes to 0. We know the limit of -1 over n squared also goes to 0. And so this term in the middle, the limit of that, must exist, and it must go to 0. So since we know those terms on either side of this inequality, the 1 over n squared, that's just one of our c over 0 forms, it goes to 0. -1 over n squared, that's also one of our c over infinity forms. C over infinity forms. So they both go to 0. So we can apply the squeeze. We can apply the squeeze theorem to that sequence in the middle, and that also must go to 0. It's forced. It exists, and it goes to 0. And you can see that from the graph here. So we have the graph of this upper portion. Is the graph of the terms in our sequence 1 over n squared. So that top curve. The bottom curve here is -1 over n squared. And you can see, when you look at this, we have our terms of 1 over n squared on the top here. We have our terms of -1 over n squared on the bottom here. And then in the middle, this is our cosine n over n squared. So you can see it has that kind of, it's oscillating back and forth like cosine does, but it's stuck in the middle. And so what's happening is the terms on the top, the terms on the bottom are all getting closer to 0. They're all approaching y equals, well, they're kind of approaching this horizontal line y equals L, or y equals 0. And what's happening is as they're getting closer and closer, all of our cosine n over n squared terms, they're stuck there in the middle, so they have to approach 0 as well. So they're squeezed. It's being squeezed to that limit of 0. All right. What do we got next? Alternating sequences. So we'll just start talking about alternating sequences here. We're gonna keep talking about it next time. But there's this alternating piece, an. We have this alternating sequence, -1 raised to the power n. And we're going to talk about this alternating term quite a bit. So it's important to kind of investigate what this term does on its own. So by itself, this is a perfectly good sequence, but you can see that it's divergent because it just alternates back and forth between values +1 and -1, but it never actually settles down and approaches one specific number. So you can see here we have it graphed here, and it just kind of alternates. The first term is -1, the second term is +1, the third term is -1. It just keeps going like that, alternating back and forth between those -1 and +1 values. And it never actually kind of approaches one specific number, so it diverges. Now just kind of contrast that with what we saw over here, where we actually did have a convergent sequence. And you can see all those terms in our sequence are kind of getting closer and closer to a height of 0. They're getting closer to 0. We don't have that kind of approaching behavior in here. It's just alternating back and forth, never approaching one specific number. And so this term by itself diverges. So next time we're gonna keep talking about alternating sequences and kind of use this result that sometimes can be helpful, where we essentially, if we know the limit of our absolute value of an is equal to 0, well then the limit of just an, our sequence an, also has to be equal to 0. So if we do the absolute value of our sequence, and we can show that the limit of this new sequence, the absolute value, is equal to 0, well then the limit of our original sequence also has to be equal to 0. So we're going to use this theorem next time, but I just wanted to kind of set the scene for what we'll be talking about. We're going to be investigating these alternating sequences where we have this sort of -1 to the power n form. All right, so let's stop there for today. We're going to be talking about sequences next time, so brace yourself. And then pretty soon we're going to be getting into series. So sequences kind of set the stage for really the main focus for a lot of what's to come next, and that's going to be series. So we're getting there. So yeah, we got a little more sequences to talk about. So all right, have a good rest of your day, and then we will see you all next time. Bye-bye.